Hi everyone, welcome at this research update from the Virtual Human Interaction Lab at Stanford. You're going to see a range of talks from PhD students and postdocs that are going to share with you the research they've been working on in the last year or so. This is followed by a short presentation by Professor Jeremy Bailenson, the founding director of vhil, who will share with you where the lab is currently at. So I hope you enjoy, and thanks so much for your attention. Hi everyone, my name is Marijn Mado and I'm currently a PhD student at Stanford's Virtual Human Interaction Lab, and I'm going to tell you a little bit about a study we recently conducted. So let me move to the next slide. So we conducted a study on children's VR use at home during COVID-19, and together with my co-authors, as you can see here below, we led this study during the outbreak of the pandemic. So we came to the study because we were really interested in what is happening now that people all throughout the US and all throughout the world are working at home, learning at home, and using all sorts of remote technologies. What is then happening with virtual reality, which seems to be kind of uniquely positioned to fill the gaps in this kind of pandemic? So a lot of journalistic articles came out talking about, the pandemic moment of VR, and will the coronavirus pandemic make VR finally like boom into reality? And we were wondering from an academic side of view to what extent this was indeed the case, and to what extent the pandemic had an influence on people's VR use. So since my co-leader of the study, Géraldine, and I are mostly interested in the educational uses of VR, we decided to focus on children's use of VR at home. So we asked mainly, what role is VR playing in households where children are sheltering in place during the COVID-19 pandemic? And this, broad question, we decided to answer using a mix of qualitative and quantitative approaches. And we set up this study starting at quite early in the lockdown, at least in the US in April 2020, until the months where there was already a reopening in place. So what we did first is we sent out this large sample survey, which 300 participants who were parents or legal guardian of children who had VR at home filled out for us. And they answered questions about their children's VR use, specifically how long they used it and what kind of uses they make of VR. Is it more gaming oriented, or are there educational qualities to it? Then a third of those participants also signed up for a longitudinal study in which they were tracked over the course of 2 months, and they filled out surveys every 2 weeks, describing to us to what extent the children's VR use has changed. And then of those longitudinal participants, we selected 20 people who we held in-depth interviews with to know more about the family dynamics surrounding VR use at home. So we have collected a massive amount of data considering these three quite elaborate methodologies. And today I'm just going to give you a snapshot of some of our findings. So one of the main things that we tracked, or were able to track, was the pulse of VR during sheltering in place. And what we found is that parents mentioned that there was a significant increase of their children's VR time since the pandemic. So they increased by, on average, 10 minutes per day. So they moved from 20 to 30 minutes per day before compared with since, which was quite, a big finding. However, what we saw in our longitudinal data is that it didn't seem to be, this is another graph, that it didn't seem to be as sustained. So what we found is that it seemed to be followed by a decrease in use, because more and more people started to mention that their children used VR less as the pandemic unfolded, and less people told us that their children used VR more. So this kind of suggested to us that there was a peak in uses when the lockdown first started, which wasn't kept up to the same extent. Well, in our qualitative data, we found a lot of reasons why this may have been the case. So first of all, we found a lot of reasons why the pandemic can be seen as a catalyst for people VR use. Here are a number of catalysts we found. I'm just going to talk about the social interaction part, because what was interesting is that now that kids or children can't meet up outside and talk to each other during the lockdown time, the shelter-in-place measures, they found a way to have social interaction with their friends on VR headsets. So they would, enter VR, and so would their friends, and this is a place where they could interact. However, there are also a number of reasons why the pandemic didn't function as a catalyst at all and could rather be seen as a competitor of using VR. And actually, on exactly the same point, the pandemic could be seen as a competitor, because a lot of parents mentioned to us that their children really desired or seek the need for social interaction. And this is why they didn't use VR, because their friends didn't have VR headsets at home. So instead, they resorted to using PS4 gaming consoles or other kind of media that would allow them to get in touch with their friends who also had this at home. So you can see that the same kind of argument goes both in favor and in disfavor of using VR. Well, we also mostly in our interviews identified some of the challenges that are associated to using VR in the pandemic moment. And I'll share just a couple with you that we found. So first of all, as I just mentioned, household access to VR is limited. It's not equitable. It's a very kind of niche environment where only some people have VR and often children's friends don't. A second thing that we found, surprisingly, was that a lot of parents mentioned to us that the hardware is actually not suitable for young kids. And we found that the mean age of children in our entire study was just a little below 10, meaning that a lot of the children in our study were 6, 7, 8-year-old, as you can see on this graph, who are quite young to be entering VR, and often their bodies weren't developed enough to be able to really reach the hand controller buttons, etc. Another challenge that was often mentioned in terms of the hardware not being suitable. The third point is, and this is more of a social cultural reason why VR may not be reaching this pandemic moment yet, is that there is a profound gender gap in the use of VR. So we found that in our large sample survey, there were many more fathers than mothers filling it out, about many more sons than daughters in terms of VR use, and also boys even used it on average a lot longer than girls. So this gender gap can be seen as another kind of issue that could be overcome to help VR become more important and more widespread. There are also some reasons for optimism, on the other hand, which was quite interesting that we found in our qualitative data as well. We found that VR, when used in households, it's often a family group activity. Children want to show their parents or their siblings what they've seen in VR. And in this way, it also functions as a conversation starter at the dinner table, especially when VR becomes kind of integrated in current affairs. And we found a number of apps that people mentioned that really allowed them to start conversations with their kids about what was happening, especially, of course, traveling while Black was very much mentioned during this, not only Corona, but also Black Lives Matter movement time that we live in. And the connection between, experiencing these kind of immersive storytelling narratives and then talking about current affairs seemed to us a very promising development, or a very promising finding in terms of VR helping to address societal issues. So To sum up our study, here's the quote again from the New York Times. This should be VR's moment, but why is it still so niche? Well, we identified in our study a lot of catalysts and competitors in terms of why this is or isn't VR's moment. And we also identified a lot of challenges, both on a technological level as on a social cultural level, as of why VR may not be there yet. But it definitely could be. And the idea of having VR in households as a conversation starter and that integrated with current affairs seems very worthwhile and interesting. So thank you so much for your attention. I would always be excited for you to get in touch if you want to know more. Definitely look out for the papers we're intending to publish with all our results. But feel free to send me an email anytime before then.
Hello, my name is Anna Queiroz. I'm a postdoctoral researcher at Stanford University, and it's a pleasure to share today with you some of our research at the Virtual Human Interaction Lab. So my background is in cognitive psychology, and I'm interested on how we can use virtual reality for learning and in education. And today we are talking about the study that was run by me with Géraldine Fauville, Fernanda Herrera, Maria Isabel Lehmann, and Professor Jeremy Bailenson about the effects of immersion on affective and cognitive learning. So to give you some context of the motivation of this study, after reviewing a lot of the research on the use of virtual reality in learning, we found that there's a long-standing interest on using that in education, but the results from the studies, they are inconclusive, favoring either VR or computer. So there is still need for more research on that area to understand better how, when VR would be more helpful for learning than using a computer. And what we know is that there are two main aspects of learning. We have the affective aspects that are related to our emotions, related to one important concept that we focused on this study that's called self-efficacy. That means our perception of our ability to learn, how much we think that we can master a content. And we have also the cognitive aspects of learning that are mainly two. We have the procedural aspects, the procedural learning, where we need to memorize the steps to perform well in a task. So for example, to solve a math equation, I'm talking about procedural learning. And we have the conceptual learning, where we are exposed to a new information and then we link that with information that we already have to create a new concept, to create a new knowledge. So in this study, we are focusing on conceptual learning because on the previous studies, the reviews that we have been doing, we can see a more variation of results when we talk about conceptual learning. And when we talk about virtual reality, we have particularly two kinds of experience. One is the immersive VR videos or 360-degree videos that are videos that were captured using a 360 camera, and then I can watch this video using a headset in this sphere. So they are more realistic than computer graphics experiences, but I can't interact much because they are real footage. We have the other kind of experiences are the computer graphics, where I can develop this virtual reality environment using digital contents and models, and I can interact more with them. So the realism usually is lower than 360 videos, but the interactivity is higher because I can move objects, I can move around the environment, I can change the environment I'm in. And so to investigate how the immersion will impact learning, we run a study with 53 female 8th grader students from an all-girls private middle school here in California. And we used two videos developed by VHIL. We have the Crystal Reef and the Coral Compass. They're both 360 videos, and we've created 2D version of it that runs on a computer monitor. And as equipment, for the desktop group, they watched the 2D versions of those videos using a MacBook Air Pro, and for the VR group, they watched the 360 videos using a Lenovo Mirage Solo headset. So what we did, we had a pre-test first on where all the students answered multiple choices questions and open-ended questions to assess their learning, to assess the baseline of what they know about coral reefs, ocean acidification. And we had also questions about self-efficacy to evaluate how they feel that they are able to learn. 3 weeks after, we had 28 participants in the VR group and 25 on the desktop group. They were randomly assigned to those groups. In a 90-minute session, they experienced either Coral Compass or Crystal Reef first, either in VR or on a desktop, and after they answered the questions assessing learning about those videos. After they watched the two videos, they answered a questionnaire about how they felt they were in the virtual environment. It means to evaluate presence, and then self-efficacy questions, the same that they answered at the pre-test. And the results we had was, even though we used a random assignment, we found a significant difference between groups at the pre-test for multiple choice assessment and self-efficacy. But what we also found was that both for multiple choices and open-ended questions, both groups learned significantly. So there was a significant difference between post-test and pre-test, and no significant difference between groups when we consider the significant difference at pre-test for the multiple choices. And for self-efficacy, we found an interaction effect of time and condition. That means that participants on the VR group, they increased their perception of self-efficacy after having the VR experiences. And participants on the desktop group, they slightly decreased their self-efficacy after having the desktop experience. And at the post-test, we found a significant difference between them. That tells us that the VR favored the development of self-efficacy. And to overcome some of the limitations of the first study, we ran the second one. This time we used a matched random assignment. It means that we took, for example, the two high scorers students, they were assigned one for the VR condition, the other one for the desktop condition, and then so on in pairs until we had all of them assigned between the two conditions. We had 139 participants, so a larger sample. We broke the session in 2 sessions of 45 minutes and with 1 day apart between them. And also we measured self-efficacy after each video to evaluate the impact of each video on self-efficacy. And we added a delayed post-test 6 weeks after they had the treatment sessions to evaluate how would be the long-term effects of the experience. And here is the design and procedure. So again, we had the pre-test to have a baseline of their knowledge on the concepts of, coral reefs, ocean acidification. So multiple choices and open-ended questions, and also self-efficacy questionnaire to evaluate their self-efficacy. 5 weeks after, so we had these 2 groups, 73 students on the VR condition and 66 students on the desktop condition. They first watched one of the videos, either Coral Compass or Crystal Reef, answered the same questionnaire as pre-test, plus questions to evaluate presence. And then on the second day, they watched the other video that different from the one they watched on the first day, and answered again questions assessing their learning, their self-efficacy, and presence. And 6 weeks after, we evaluated again those variables using exactly the same test we used at the pre-test. And as a result, what we found was this time there was no significant difference between conditions at the pretest. That means that the matched random assignment was successful. We found for the cognitive assessment, the multiple choice and open-ended questions, a significant increase on their learning from pre to post-test on both groups. For multiple choice assessment, there was no significant difference between groups after treatment, but we found that for the first time on the open-ended or qualitative assessment of learning at the post-test. So participants on the VR condition showed higher score for learning than participants on the desktop condition. And for self-efficacy, we found also a significant difference between groups after treatment, showing that participants in the VR condition, they showed an increase in their self-efficacy after the experiences, while participants on the desktop condition, they decreased slightly their perception of self-efficacy. And for all those variables, we couldn't find any significant difference between groups at the delayed post-test 6 weeks after. So those results, they tell us that, for example, the results from study 1, they replicate Makransky, Burgood, and Myers study that also compared VR to computer desktop. And they also haven't found any significant difference between conditions for learning, but they could find for self-efficacy post-treatment and with participants in VR having a higher score in self-efficacy. And the question is why the immersion would increase self-efficacy. And some of the explanations we think about are, we know already that VR increases engagement and enjoyment, and those are two components of self-efficacy. They impact positively self-efficacy. Also, we know that VR can give greater control to the students, and maybe this feeling of greater control, they can control where they are looking at and what they are learning, impacts positively self-efficacy. And also we know that VR increases agency, and this maybe can positively impact self-efficacy, but further studies are needed to investigate those. And when we talk about conceptual learning, what we think is that because we use the 360 video, immersive VR video, it lowers the cognitive load compared to to computer graphics experiences. So that favored learning in VR because it required less brain resources to understand what they were receiving, the information that they were receiving, than if they were in a computer graphics environment. And so as conclusions, we have that there is a positive impact of immersion both on self-efficacy and on qualitative learning after treatment. But those effects, they do not persist 6 weeks after, so no significant long-term effect of condition that give us evidence of immediate positive impact of increased level of immersion on conceptual knowledge and on self-efficacy. So as future directions, we suggest using large samples in the next studies. We use a more diverse population because we had only girls from a private school in California on those studies, so we suggest a diverse population. Also, we suggest studies focusing on multiple immersive virtual reality exposures, so to measure how the long-term effects of these multiple exposures would be, and keep accessing the delayed retention, and also having multiple learning assessment methods. Here we use multiple choices and open-ended, but also we can add other kind of methods to assess learning and have a more comprehensive measurements of learning. So thank you so much for watching. And if you have any questions, please contact me at acmq@stanford.edu. Bye.
I'm a graduate student at the School of Education. I work with Roy P. And my goal for today's presentation really is to try to give a super quick bird's eye view of some of the research we have been doing at the School of at the GSC, really trying to understand what we know and what we do not know about VR and virtual learning environments. This is kind of how we kind of organized the entire spectrum of virtual learning environments. Again, we put this against two axes of perceptual immersion on the top and then interactivity on the left. And really, we wanted to zone on to immersive VR in headsets, really trying to understand what were the educational merits of immersive VR in headsets. But in order to do that, we thought it would be very important to lay it out in context of the broader spectrum of virtual learning environments like desktop-based VR simulations, games, mobile VR that is accessed through smartphones, because all of these have been extensively studied and extensively used in educational contexts over the last few decades. And it was really important for us to locate immersive headset VR in context of these other technologies. So the first one is immersive VR. And when I say immersive VR, I'm talking about 6 degrees of freedom. And the very first kind of high-level finding we had is most VR experiences in education, looking at K-12 and higher ed across the world, most of these VR experiences accessed in real-world environments, and most of the studies done have been done on off-the-shelf consumer products. We really found that, the findings on immersive VR delivered through head-mounted displays shows the findings are very conflicting. We think that these conflicting results may be related to the fact that almost all research involving VR and education has featured learning content which learning scientists are using and it's usually existing learning content that is being used that has not been largely designed by educators, or alternatively features content built by educators but does not really have the budget or VR expertise to build content which exploits the unique experiential potentialities of VR. So we think that there is certainly a disconnect between two schools that may be trying to ask very similar questions here. Certainly still very interesting findings on the other side of virtual learning environments. And I'm thinking of these moves and these massive kind of online multiplayer, sometimes interactive virtual simulations that are not accessed on a headset, but rather on a desktop, on a laptop, on a computer. And VR certainly seems to be triggering intrinsic motivation, engagement, joy. It improves confidence and self-efficacy levels. And this is largely because most of these studies are very deeply rooted in curriculum design, and it has been just critical in the success of these programs and these studies. The integration of the learning science theory in a lot of these papers is what really pushes the technology beyond the initial wow factor and really allows you to demonstrate learning outcomes that are not due to the glamour or the novelty or the newness of the technology, or as Morgan Ames calls it, the charisma of the new technology, but it is largely due to underlying and very fundamental integrations of learning science theory. The final category was mobile VR, and this one is very interesting because the research is just not evolved here. Studies are not very rigorous. We were unable to find too many research papers that really talked about mobile VR deployed in real-world learning environments and really studied the educational outcomes of these technologies. But mobile VR has certainly received a lot of media attention. It has a lot of hype around it, especially in the early days of Google Cardboard and other kind of accessible and affordable quote unquote VR devices. By far, this is the most affordable and accessible form of head-mounted display rendered VR today. Almost 60 to 70% of K-12 institutions in the United States today have used mobile VR. A lot of papers have shown that these devices cause motion sickness. If used for long periods, they can be gimmicky in the sense that there is overheating problems. There are just issues with the infrastructure of integrating these sorts of technologies in the classroom. And we think it's really important to be also asking and studying these questions alongside the learning outcomes that. So just to summarize, what we're looking at in our lab and through my dissertation research too right now is really trying to develop an entire VR curriculum. We want to do more long-term studies with immersive headset headset VR. So 6DoF, kind of the top of the range VR, as these devices also become more consumer affordable, with devices like the Oculus Quest coming in the last year. There's been a huge adoption of Quests in schools across the nation and also across the world. My goal through my research is to unpack these features of the experience that differentiate between having an effect on belief versus having an effect on behavior.
Hi, my name is Géraldine Fauville, assistant professor at the University of Gothenburg in Sweden. And up until 2 months ago, I was a postdoctoral researcher at the Virtual Human Interaction Lab. I will share with you the results of our study on aquatic VR and vection. In this study, we are focusing on the perception of movement. So our vision, audition, inner ear, the receptor on our skin, in our muscles and joints constantly help us make sense of our movement in the world. The integration of all the sensory cues induces vection, which is the conscious and subjective experience of self-motion. A popular example of vection induced by visual input is the train illusion, which occurs when a person sitting on a stationary train observes the neighboring train leaving the station, inducing erroneous vection. Vection has been studied for more than 150 years, and subjects have been placed in different positions, standing up, sitting down, or even laying down on their back on hyperbolic flight, creating microgravity. Participants have also been subjected to wind blowing in their face or on their whole body to see how the somatosensory system of their skin contributed to vection. They've been asked to move in different ways, such as walking or making breaststroke movement. Vection has also been studied in VR, as the illusion of motion is an important component of the immersion. Vection in VR is also linked to motion sickness, and according to the sensory conflict theory, motion sickness seems to be linked to vection as it is caused by conflict between different sensory inputs. So in this paper, we investigated vection and motion sickness in VR, but we did so in a new environment. For the first time, this study utilized waterproof VR head-mounted displays to understand how being immersed in water while simultaneously in VR impacted vection and motion sickness. And this study was made possible through a collaboration with the VLES company that developed the equipment used. This study was run at a local swimming pool, and 38 individuals participated and were randomly assigned either to the ground condition or to the water condition. And in both conditions, the participant watched the same VR activity. The virtual environment was displayed on a Samsung Galaxy S8 that ran a custom operation system designed by VLES Technologies. The VR experience was about 5 minutes long and brought the participant underwater for a 300-meter-long drift dive in the ocean at a virtual speed of about 1.7 meters per second. In the ground condition, the participant watched the VR activity while standing and were invited to turn around to look all around them. In the water condition, the participant watched the VR activity while floating on the water and were also invited to turn around. The participants in this case were tethered to the researchers to prevent them from drifting or swimming away. In both conditions, we measure vection through the perceived body displacement technique known as egocentric distance estimation. This technique quantifies how far away from the initial position participants thought they were when they completed the VR experience. So at the end of the VR activity, we instructed the participant to keep the headset on, and we asked them, how far in the physical world do you think you are from where you started the VR activity? The well-established simulator sickness questionnaire was used to measure motion sickness through 16 questions surveying the occurrence of motion sickness symptoms such as nausea or stomach awareness. The analysis revealed a significant difference of egocentric distance estimation. When asked how far they were from the initial position, on average, the participant on the ground thought they had moved less than half a meter, while participants in the water thought they were almost 3 meters away from the starting point. So this indicates that vection is greater in water. There are a lot of ways to connect these findings with the existing knowledge about vection. First, neutral buoyancy in water mimics microgravity. We know from previous research that when in microgravity, the body relies more heavily on the visual inputs to evaluate self-motion. Researchers also suggested that microgravity decreases the conflict between the visual and vestibular information. And in this way, our finding aligns with previous studies on the positive impact of microgravity on vection. The somatosensory input on our skin was different for our participant in the two conditions. The role of the somatosensory system has been explored by scholars by blowing wind on their face of the participant. And the somatosensory input has been shown to trigger greater version. So in our case, the water against the skin of our participant might have played a role in increasing vection measure compared to the ground condition. Finally, the biomechanical information provided by the muscles and joint have been studied mainly in relation to walking or breaststroke movement. And researchers have shown that breaststroke movement enhances vection compared to passive standing participant. In our study, some participants in water engage in swimming movement that could have contributed to the greater vection. Concerning motion sickness, a motion sickness score was created based on the mean of the 16 items from the scale. A test was conducted, but no significant difference was found for the motion sickness score. Exploratory analyses were conducted on individual questionnaire items, and we realized that eye strain and stomach awareness were greater for the ground condition, while difficulty to concentrate and increase salivation were significantly greater for the water condition. However, these differences are not significant after applying Bonferroni correction. So we did not observe any significant difference in motion sickness, and it is important to note that the simulation sickness questionnaire that have been widely used was used for the first time in water. So we argue that some items might not be adapted to this kind of environment. For example, the item increased salivation, that is normally a sign of motion sickness, was higher in water than on the ground. Since the participant in the water had a mouthpiece in their mouth, we can imagine that this had an impact on their salivation that was not especially related to motion sickness. So there is a need for an adapted or revised scale for water condition. To conclude, I would like you to remember these 3 points concerning this study. First, the paper provides a tested method to study VR while immersed in water. We also have the very first finding on the impact of being immersed in water on vection, and this opens up new research questions. And finally, this study also raised some questions concerning the measurement tools that can be used in this new environment. And with that, if you are interested in knowing more about this study, feel free to contact me via email or on my Twitter account. Thank you.
Hello, my name is Jeremy Bailenson. I'm a professor at Stanford in the Department of Communication, and I run Stanford's Virtual Human Interaction Lab. I am thrilled to be here presenting today, and I want to thank VR Days Europe for hosting this amazing group of speakers that we got to hear in this session. And it's my privilege to be a part of this group. What I'm going to do today is give a little bit of background about myself in the lab, then reflect upon and assimilate some of the talks that we've heard today, these amazing talks we heard today in this session. And then with the time left over, I'm going to talk a little bit about some of the current work we're doing in the lab that wasn't covered in the talks that we heard today in this session. So to start out, a bit about me. My PhD is in cognitive psychology. In 1999, I switched fields to leave cog psych traditional and moved to UC Santa Barbara, where I learned how to build the hardware to build VR, how to program the content, and how to run experiments on social issues ranging from interaction with other people in communication to learning and training to understanding engagement and perception, all sorts of high-level topics that we're studying with VR. And that was in 1999. I moved to Stanford in 2003, and since 2003, I've had the pleasure of working with brilliant scholars like the ones that you just heard from, and we've been studying how VR affects the mind, what applications work inside VR, and what are the implications of using VR, both good and bad. So moving on to the talks that we just heard, I'm going to start with, I'm going to go in order of the presentations and start with Marijn, who gave an amazing presentation on a study that is impressive, not only because of its depth and its thoroughness and its thoughtfulness, but because of how quickly my colleagues turned around this study. And so shelter in place happened in late March here. And as a parent, I have a 9 and a 6-year-old. I foolishly believed that I'd be able to just easily fold my kids into VR, because like many of you at this conference, I've got all sorts of hardware at home and access to the best colleagues who build educational content, etc. And I really struggled as a parent finding good demos for kids in VR. Not that they're not there, but I struggled to find them, and more importantly, trying to figure out how to embed them into a curriculum. And really, that was hard for me to do as a parent. And eventually, I just gave up. And we were talking about this at lab meeting, and Marijn and Géraldine and Anna and others, they immediately figured out how to start running this study almost immediately, quick turnaround on getting IRB approval, and then, you know, designing a multi-method survey methodology and longitudinal repeated contact with these parents, and then finally doing these in-depth interviews to really get a snapshot of what did VR do during COVID. And what I love about this study is it's going to give us a moment in history, and it's going to document this moment in time wonderfully, because we were able to get this data in real time. But also, you know, starting to understand what's working about educational VR, what's not, and it really gives us feedback and take-home messages about what to do as designers in the space, as educators, and as parents. So really excited about this study and looking forward to publishing it. Yeah, you guys are getting a bit of a sneak preview on it, and we're still in the process of writing it. So moving on to Anna's presentation, Anna presented what is likely the most rigorous field study in the history of VR of education. You know, close to 200 kids. These are all, as you know, middle school girls, but unbelievable to run 2 studies embedded inside schools where, you know, the researchers were there every time and looking at multiple time points. And so what's missing from a lot of VR studies is understanding the effects of VR experiences when you project out longitudinally, and how long do these effects last. And so, you know, the amount of rigor it took to bring VR into these schools and to be with them, not just at one time, but at many times, to run 2 studies with similar measures to get replication. So we're sure that the effects are there. Just an incredible Herculean job by Anna and colleagues on this. And, you know, the finding that we're just absolutely excited about, and, you know, one would predict this from the literature, but this is the first time anyone's shown it so robustly, is this notion of self-efficacy, that if you take a girl in middle school and you put her in VR and she's getting to do science, meaning she's getting to be there and to go underwater with a scientist and to actually see these things in a way that's active, what Anna's results is showing is that these kids now can have an easier time of seeing themselves as scientists. VR removed this blockade compared to video that I couldn't be a scientist. And so just stunning data showing on the effective learning side that VR can give students self-efficacy, the belief that one day they can do science, and just really exciting data on a really rigorous scale, both in terms of sample size and looking at multiple times. Next, we'll talk about Aditya's presentation, and Aditya, working with Roy P. and myself, has done just a great job at assimilating the VR educational literature, both in terms of what we know finding-wise, integrating educational theory, and also leveraging what he knows from having built a lot of content himself. So really a nice understanding and assimilation of where we're at academically in terms of what content is there and how you can build content while leveraging, you know, bedrock learning science when building it. Géraldine presented an incredible study that to this date, how she was able to pull this off, how she and her colleagues were able to pull this off. I mean, think about how hard it is to run a VR study. Now think about how hard it is in general to do things like run experiments when people are in bathing suits and underwater, and she combined them, and she had got subjects to come in, go into pools, put underwater VR in their face, and collected amazing data on how this experience changes people. And I want to take a little bit of step back. And the first time I ever did underwater VR, it was, you know, 3 years ago, I think 2017, and the folks that make the Bailenson headset, they brought me a really early prototype, and it was a rainy day in December. I remember it really well. We went to the pool here in Redwood City, and there was no one in the pool because it was cold and rainy. And I put on these goggles and I floated on my belly and was just experiencing this utterly mind-blowing, what Géraldine likes to call double immersion. You're immersed in VR, now you're immersed in water. And at the end of this demo that I did, this demo, you're actually floating through space. If you were to ask me before I took the goggles how far I moved, I probably would have guessed 15 to 20 meters. And in essence, I hadn't moved at all. But this notion of being ungrounded from the physical world and floating on water, you lose your frame of reference. And it was really jaw-dropping. And I before that moment in that demo, I'd always thought that underwater VR would be something that's gimmicky, but quite the contrary. It was just, it was an experience that really affected me. And so when Géraldine expressed interest in running this study, I was super excited that she wanted to take the lead on it. And the amount of work she had to do theoretically before even getting to logistics to understand, you know, she's trained as an educational technologist and a marine scientist, but to figure out the literature on vection and on all sorts of perceptual issues, it was a journey for her, and I got to learn alongside her, which was exciting, just from the updates that she would give me. But then figuring out how to get this study run logistically and run this huge team, and the data she presented, you saw the data, utterly incredible. That when you're in water, you believe you're moving. And this idea of you can cause someone to believe that they've moved 3 or 4 meters, they really think they've moved, but they've in essence stood still, you know, really neat for understanding the brain and understand the effect VR has on perception. But then just, you know, in terms of just the wow factor, like, you know, for those who haven't tried underwater VR, it really is incredible. And this notion of moving is just a great study. So again, that one's not published either. It's under review, so you guys are getting a bit of a sneak preview here, but super exciting research there. The next study I want to talk about is a paper that came out today for me. Today is when I'm recording this video, which is October 16th. A paper came out in a journal called Scientific Reports, and this is work that's led by Mark Miller, and it's about privacy. And in this study, we had 511 subjects. This was a study we ran in a museum. And in the museum, they put on the goggles, and each of them saw 5 separate 360 videos. The 360 videos lasted 20 seconds, and we recorded all of their tracking data, how their heads moved and how their hands moved. So even though we're doing 360 video, we were using the HTC Vive, and we got 18 degrees of freedom, recorded it at a high frequency, recorded all of the tracking data. The point of this paper I'm presenting now is to understand how identifiable VR tracking data is. And so what we know from the nonverbal literature is that, it's easy to control what you say. As I give this talk, I'm trying to pick out every word perfectly and to frame it in the right way, but it's hard to regulate your movement. Your movement is kind of automatic, and nonverbal behavior is tougher to think about. It's just something that we do. And lots of research showing that if you want a true window into someone's intention, study what they do nonverbally, because we can regulate what we say, but nonverbal leakage, to coin Ekman, is something that's hard to pin down. So in this study, we wanted to ask the question, in a large sample, 511 people, how easy is it to identify someone from their nonverbal footprint, from the digital footprint that's captured from VR? And a lot of VR companies, their privacy policy basically states, we're going to remove your name, we're going to take your name off this file, and then this tracking data, this very large file, to give you sense with 18 degrees of freedom, pitch on roll X, Y, and Z of the head and both hands. After 20 minutes, the data file is so large, it's over 2 million data points about your body language. And lots of great work from early scholars have shown that if you've got this nonverbal data, you can figure out medical conditions of people. Great work by Susan Persky there. You can figure out the type of student somebody is. Great early work from Skip Rizzo. This nonverbal footprint captured in VR is very predictive. And what we wanted to figure out in this study is, knowing that the nonverbal footprint is very predictive, what is the ability to recognize somebody from their body language? And so what we did is we took the nonverbal data from 511 people, and Mark Miller did a ton of math and computer science on data science on figuring out, can you recognize someone from just a thin slice of their body movements? And what Mark discovered, and a paper that came out today in a journal called Scientific Reports that you can all download, is that with 5 minutes of tracking data, meaning 5 minutes of the data of you moving your body inside VR, in a sample of 511 people, you can be identified with 95.3% accuracy. Chance is 1/5 of 1%. The machine learning algorithms can pick you out of a bucket of 511 people with 95% accuracy with just 5 minutes of data. And the take-home message from this is that you can identify someone very easily from tracking data, and taking their name off of that data file really doesn't do much in terms of protecting your privacy. So to conclude, all the data we talked about from the studies about education, from the earlier point of this presentation, was all about the wonderful, amazing, incredible use cases of VR, and we've seen a lot of that, I assume, at this conference. I don't want to close on a dark note, and I am optimistic for the future of VR, but privacy, for those of you building applications, running studies, privacy shouldn't be an afterthought. It should be something that's thought of early on, because the data one can collect in VR tells a lot about who you are. So again, I want to thank you, those who are watching this video, as well as the organizers of VR Days Europe. I really appreciate getting to have a whole session just about the great work my colleagues are doing in this lab. And I want to thank you for your attention.